Hello and welcome back to Calculus 1, section 3.3 on derivative rules. So we learned that the definition for the derivative using the limit definition is the limit h goes to 0 of f of x plus h minus f of x divided by h. And you compute, and then eventually you have the function at the end. It's a lengthy procedure. It's a 2.3 procedure. This will definitely be on the exam. It's not going to be called derivative. It will just ask you to calculate the limit of a difference quotient. And as I said in 3.1, all we did is we gave it a name, right? Because you learned the entire calculation in 2.3. Now, what we are going to learn tonight, I'm going to offer a whole bunch of formulas, the full bag of formulas, and then you will make effort and conscious decision, right, to memorize them. You were faced with these choices before. And generally, people made them for you. Now, since you are all, grown up, you will hopefully make that conscious choice. So, remember 3 times 5 equals 15?
No.
Right? The rest of you. Remember 3 times 5 equals 15, right? At some point, you were supposed to memorize that and learn it. Why? For convenience. Now, when you are second grade, memorizing or third, or whatever, I don't know which grades, one of the grades.
7th grade. 12th grade.
You are guys setting me up for all these awful things to say, and I'm just swallowing and burying this poison deep inside. That's why I drink. Anyway. The voice just keeps going. Anyway,
just let it out.
Anytime I stop like this, I just want to follow through and see what they have to say. A lot of them, many. Yeah, 666 of them. Constantly. Anyway, what I was talking about?
Memorizing.
Yes, never 3 times. But thank you. See. You would think one of them will just say 3 times 5. Anyway, so 3 times 5 equals 15. And what do we do with that? You memorize that 3 times 5 is 15 because it was convenient. You did not want to go and say every time you need to add 5 threes to go 3 plus 3 is 6 plus 3 is 9 plus 3 is 12 plus 3 is 15, right? So there's this short way of writing 3 plus 3 plus 3 plus 3 plus 3 as 3 times 5, and you get 15. And you sat down and you memorized 100 of these formulas, right? Because 1 times 1 is 1, and 1 times 2 is 2, and 1 times 3 is 3, right? Eventually 4 times 8 is
32.
32. Yes, got you. Right? So, I know. So, you memorized all of these, and now we're going to do the same thing. Can you do derivatives using this formula? The answer is yes. What I'm going to introduce now are a whole bunch of formulas which are all shortcut method. So just like 3 plus 3 plus 3 plus 3 plus 3, so 3, 6, 9, 12, 15, that's the long way of doing it. That's compared to like working out derivative using the formula. Or you memorize 3 times 5 is 15. Now I'm going to just say, if the function looks like this, the derivative is that. If the function looks like this, the derivative is that, and so on. So we're just going to learn a whole bunch of these formulas, which you can choose to memorize, in which case the rest of the calculus, differential equations, and everything else is going to go smoothly, or you can choose to ignore, and then good luck with, every time you need the derivative, right there you are, Yes?
So will we ever need that equation on the test
No.
after you get the shortcut?
No. That's the idea. To retire this equation so you do not have to go through the horrors of computing it, right?
Yeah.
And today's lecture is supposed to retire this. Now, we are going to use it here and there to prove certain things, but it's going to show up on your first exam, right? And then it really doesn't have to show up again until you do the proof for partial derivative in Calculus 3. And then I don't think after that shows up. So let's go with the first one. Well, before we do that, let's talk about notation. There are few ways to denote the derivative. There is the f prime of x, the y prime, the original Newton notation, y with a dot on top. You might see this notation if you are mechanical engineering and you have really old professor. They would be the ones keeping the tradition of the dot from Newton's era. And Leibniz notation, which is my favorite, which is dy dx, which you can also write as d dx of f of x. That's my preferred. However, we will be using this, and this. You use this one only when you are extremely lazy. The other notations are better. All right. So now I'm going to say, because we already seen it last time, if y is equal to 1 over x, we use the f of x. So f of x equals 1 over x, you said f prime of x is equal to negative 1 over x squared. So you have one line in which you introduce the function, and then in the next line you introduce the derivative. Now, we did this calculation last class, so we know that this is the derivative, right? It is not something that you are memorizing. You can memorize this because it is going to be frequent in your Calc 1, 2, 3, and differential equations to find the derivative of this function. You will do it many times. But right now I am focusing on the notation, and please note that you have two lines, right? The one line for the function and another line for the derivative, and each one is labeled which one it is, right? Now, the same question, we can say y equals 1 over x, y prime equals negative 1 over x squared, and that would be, using the y instead of using f of x. And finally, the best notation is to say the derivative of 1 over x is negative 1 over x squared. Hopefully you see that this is the only one where you get to write in line, right? You're writing in line, and the way you read this one is you say the derivative, I'll put the red of because there is a times right there. 1 over x is negative 1 over x squared. Well, I can do the is. I can do this in black. Is the derivative of 1 over x squared is negative 1 over x squared. There we go. So that's the way you read this. So this d dx is the operator that tells us that we are supposed to differentiate. We are supposed to take the derivative of 1 over x, and this procedure here we saw that earlier will give us as the answer negative 1 over x squared. So this is just a notation. Now you're going to pick your favorite, and then you can stick with it. I don't care which one of these you provide on the exam, because all of these are correct. The reason why this is my favorite is because I can see the independent variable, because I have d over dx. It's useful later for Calc 3 a lot. And then also it's in line, so I don't have to use two separate lines to show the derivative and so on. So, but again, you can pick any of the three to be the way you do derivatives. So let's take a look at those formulas. The first formula is going to be that the derivative of a constant is 0. Last class we learned that for every flat piece, right, of the graph, we drew the derivative on x-axis. I asked you why, and you told me last class that constants don't change, derivatives measure change, so change is 0 for the flat pieces. Now, flat piece is c. See, this c is a constant. So technically what you are looking at with this formula right here, you are looking into an example, what is the derivative of, let's say, number 3, right? And the answer is 0 because graph. As you draw the horizontal line through 3, because that's the value of c, of a constant. So as you write that in there, you see that it never changes. Right? It's always the same y value, 3. So since there is no change, it's always flat, right? You would say that the derivative of the constant is 0. And that's your introductory formula. Next formula is going to be the derivative of x to the n is equal to n x to the n minus 1. Now this formula covers a lot of stuff, a lot of functions. Which one is the obvious?
Exponential?
No. Exponential. Exponential has a number raised to x. This one is
How about x squared?
x squared. That would be maybe the most obvious one to use, x squared. You can use x to the 9, x to the whatever. So x squared, x to the 9, x to the 5, and all of these guys, they belong to family of what kind of function? Polynomials. Beautiful. So if I have n, right, to be the whole number and to be positive, so n, let's do it this way. If n is positive whole number, we have x to the n to be polynomial. So this rule that you see up there is going to work for any polynomial you can come up with. Maybe you have negative 16 x to the 3. Great, it's going to work with this. The next is what happens if n is negative whole number. What is x to the n? What type of a function? Nope. Yeah, 1 over x. What do we call those functions?
Rational?
Rational function. Very good. So if it's a negative number. Now we'll do examples for all of them. And finally, if n is a fraction, we have what? We have the root functions, so we're going to call this radical. So radical function. So these are your three cases for n, and as you can see, one rule of differentiation covers polynomial functions, rational functions, and radical functions. So this formula, right? Really, really good to know, this one. So let's take a look at all of these examples. Now, obviously, we start with x to the 7, let's say. That's clearly, right, positive whole number, positive integer, and we get to use the rule. Now, the rule says n, x to the n minus 1. That's what the rule says. So what's my n? So 7, x to the 6. Beautiful. Now, if you are to sit here and use the rule with the limit, right? You have to raise x plus h to the 6th power, right? And you have to to the 7th power, and you have to, right, go and simplify that.
How'd you get 7x to the 6 for that?
Use the rule. If n is 7, we cool?
Yep.
Good. Next example is going to be the derivative of 1 divided by x to the 3. The first order of business is to rewrite this. Now, obviously, you will be rewriting this in your head later on when you get practice. Right now, you are rewriting this into the derivative of what? X to the negative 3. Very good. And now, the same rule applies. Drop down the exponent as is, and then take away 1, so negative 4. So now we have negative 3 x to the 4th as the answer. So stare at this, make sure it makes sense, and run it against the formula. So far, we covered two formulas: derivative of a constant is 0, and these types of derivatives. So the next question here is the derivative of 5th root of x squared is what? So that's a 5th root of x squared. So what do we do?
To the 2/5.
Beautiful. We rewrite this as x to the 2/5. We drop down 2/5, x to the negative 3/5. And now we can do some algebra over here. We have 2/5, 1 over x to the 3/5. So we don't have any negative exponents. The reason why we don't like negative exponents is because we can't compute them, right? You can't calculate 4 to the negative 2. You can only calculate 4 squared. So we use this algebra rule to change x to the negative 2 down to, right, 1 over x to the positive 2, and then you can compute. So that's the reason why we don't like it for the negative exponent. And now, in one view, you have all three flavors of x to the n. With the first example up there was a polynomial, the second example was a rational function, and the third example is a radical function. Now, obviously, those exponents values change, and then it slightly changes the result, always according to this rule. Okay, next one. Yes.
Do I have to write it in that form or just leave it as 2 over 5 x log 5?
No, you have to, yeah, no negative exponents. No negative exponents. And I had the last night, I had the question in class, do I have to simplify? Well, where are my computer science people? You do. The rest of you, you don't. Okay? So I just need to make sure that I visually tick off all of you that are computer science, and if you don't simplify, -5 on the test. And the rest of you, you can do whatever you want. All right? Why? Why such a terrible policy? Like, why are we singled out? You remember from simplifying, what I explained in class. You optimize your software if you have less mathematical operations, right? So simplifying mathematical expressions gets computer processor to compute less numbers. There are less steps, which in turns make it work faster. So anytime when you hear someone say, oh yeah, video game is great, but it's terrible, it's not optimized, it's terrible, well, yeah, there's going to be some programming that you have to do in the back so the computer can. So it's not just making the hardware, double the hardware or whatever. It's also make sure all of your mathematical formulas inside your code are all simplified for the minimum amount of computer operations so that the processor can plow through that faster.
So it would be like putting these shortcuts into your code instead of having it use the original formula.
Well, yeah, but if you consider, right, first of all, we can't compute negative exponents, right? That doesn't exist as a computational method.
Exceptional.
Right?
That'd be an exception.
Yeah. So, I mean, people to write code, no, since, right, you guys are learning, obviously. So yes, you do have to simplify for those reasons, and we get to single out computer science today. It's awesome, right? The rest of you, hold on, wait, I got I'm gonna get all of you covered, right? Next one. The derivative of e to the x is e to the x. Awesome, right? This is the only function that returns itself as a derivative. All other functions will go to something else, right? Remember now, let's say you have a number 3. Number 3 is only equal to itself, and then number 3 is not going to be equal to anything else. So this is the only function that it's equal to itself when you take the derivative. Every other function is going to go into something else. Now, being that that's not that interesting, we're going to have upgraded version, which is going to be the derivative of e to the ax, meaning, and then the answer is a e to the ax. So the upgraded version of this formula, I put this one on a cloud, because most of the time you see actually this one, not the one on top. This allows you to take the derivative of, let's say, e to the 3x. So you have to find the derivative of e to the 3x. And what's the answer? Very good. I gave you enough time. All you do is Control-C, Control-V, and then this one drops in front. I mean, come on. How fast? Done. Right? Fast. Fast. What is the derivative of ln x? It's 1 over x. I was supposed to be red and in the bubble. No. There's not much I can say about this. It's just formula you learn and you move on. Now, the next two formulas belong to other functions we already learned, but because they show up so much, you might want to memorize them. Do you have to memorize ln? Yeah, if you don't want to go through the limit horror up there. So all of the formulas I listed so far, which is technically 2, 3, 4, those 4 formulas are must know. Now we're only covering half of these things because there are trig functions coming up in a different section and so on, so we'll do much more than this. Today we kind of scratch the surface. Is there a cool title that I can say useful or whatever, just good to know. Good to know. What is good to know? The derivative of 1 over x is negative 1 over x squared. Is this formula something crucial to memorize? No, but 1 over x shows up so much that if you know the derivative for it right off the bat without going, oh, it's 1 over x. That's x to the minus 1. Drop the minus 1, x to the minus 1, which gives me minus 2. And I'll take the x to the minus 2 and put it down to x. You see that, right? If you just know it what it is, you just plow through the whole procedure. So you will use, right, to prove this, you will use x to the n rule, but if you just have it memorized on what it is, then you don't have to mess with the x to the n rule, the second one I listed, to come up with this. So that's one that is going to be pretty much everywhere. And the second one is the derivative of square root of x. That's another one that is all over the place. And if you just memorize that it's 1 over 2 root x, you are good to go. You also use x to the n to prove this formula. So you can, now, you can, we can prove this. Let's prove this. Proof. So what do I do? Well, it's not really proof. I need to crank the limit. So let's do it this way. Instead of doing that, I'll go this way. There we go. So use this one. So what do I have? I have the derivative of x to a half, because that's what square root of x is. Square root is 1/2 exponent. So now I'm using x to the n formula for derivatives. So kick out 1/2, that's the exponent, times x to the 1/2 minus 1. Well, that's equal to 1/2 x to the negative 1/2. Then this negative drops the x in denominator, and half gives it a root. So 1 over 2 root x. Right? The negative exponent kicks the base in the denominator, and then 1/2 exponent is square root, so all of this works out together. So these are good to know formulas. You see that you can obtain them from the other rules, but it's nicer if we are quicker with them. And now we are going to cover the 3 rules of linearity 4 derivatives, they will be exactly the same like the ones you've seen in limits. So, properties of derivatives. Number 1, if you have the derivative of 2 functions that are added, you can take individual derivatives of each of the functions and add their results. This is very useful when you have multiple terms in the function and you just know that each term of the function will be treated separately. Partner in crime over here, number 2, is the one with subtraction. So f minus g would be the derivative of f minus the derivative of g. So these 2 rules work together, and you use them to separate the terms, and you can take derivative of each term individually. Last one on this list, number 3. Just like limits, it tells you that you can kick the constant outside of the, what do you call it, the derivative, and then multiply that constant later. So if I have the derivative of some constant c times f of x, I can kick the constant outside and focus my derivative only on f of x, and then when I am done with the derivative, multiply the c into the problem. That one is nicest to be demonstrated first. So number 3 over here. What is the derivative of 6x to the 5? Right? So the way we do this is we kick 6 out and we just focus on the derivative of x to the 5. And what is the derivative of x to the 5? Excellent. So the derivative of x to the 5 is 5x to the 4th, because you are using that rule that subtracts the power, right? And now you do times 6. So you get 30x to the 4th. So only constants. You can't do this with a variable, with x or something like that, right? You can only do this with a constant. You can kick it out. When you kick it out, you deal with the derivative, and then whatever you have, multiply by the constant again. Now, obviously, once you start doing the homework and you get comfortable with this, you will immediately go, oh, 5 times 6 is 30, and then just minus 1 on the 5, and it's 4. So you will be skipping all of these steps, obviously, once you are more comfortable with these things. Now, to tie in the other 2 rules with this one, we can take a look at the derivative of 2x squared. Let's go with 3x squared. 3x, because I see some of you are using pens, so when I change it, you have to scratch that. So 3x squared plus, let's go with 10x, and let's do minus 2 square root of x, like that. So now this is where all 3 rules kick in at the same time. You will only focus your derivatives on x squared and x and root x, and then whatever answers you get, you will multiply those answers with 3, 10, and -2. So you kick 3 out, and you take the derivative of x squared, plus you kick 10 out, and you take the derivative of x, and you kick out negative 2, and you take the derivative of square root of x. And you know each one of these derivatives separately. So 3 times 2x, the derivative of x squared is 2x. You drop down the 2. You're using x to the n rule. So you drop down the 2, and then 2 minus 1 is 1 as the exponent, so 2x. Plus 10, and the derivative of x is 1. Why is the derivative of x 1? 1 minus 1 is 0, and then x to the 0 is 1. Very good. And now you have this negative 2, and you memorized that the derivative of square root of x is? Yes, beautiful. And now you just simplify all of these things. So 6x plus 10 minus 2 and 2 will cancel, 1 over root x. And that would be this problem. Now, guys, when you do a lot of homework, you will go from here directly there, because you will immediately say, oh yeah, 2 times 3 is 6, x drops to just plus 10. This will cancel with the denominator, right? There are a lot of these cool things that you can quickly learn and do. Okay, one more. The derivative of 4e to the 2x minus 6e to the negative 3x plus 10 is what?
Plus 18 negative 3x plus 0.
Welcome to Calculus1. Just look at this, you know the answer. So you should use that knowledge. Next thing dinner coming up. What's new? Well, the derivative of. Some people might leave, more food for you.
Is that your strategy? Get the derivative of the metabolism of your stomach.
Yes, you actually can, because it will measure the change at which, yeah, you can calculate efficiency and stuff like that.
And it would just make them not want to eat.
Great! We kick 4 out. We focus our derivative of e to the 2x. We kick out negative 6. We focus our derivative on e to the negative 3x. And then I'm just going to say plus 0, because we know the derivative of 10. Right? It's a constant. It's just flat. So no change. So the derivative of 10 is 0. Now, if you have a number in front of x for e to the ax, that number just flat out drops down. So we have 4 times 2e to the 2x minus 6 times negative 3e to the negative 3x, and now 8e 2x plus 18e to the negative 3x. for computer science. 8e to the 2x plus 18 divided by e to the 3x. Right? I mean, well, what's fair is fair. The rest of you are right here. Yeah, we're gonna do. People are logging on, changing major right now. Don't. You have the highest starter salary when you graduate. So there's a reason. You know, the surcharge of 20K, extra step in every problem. Okay. Beautiful. These are shortcuts. These are shortcuts for derivatives.
So if you didn't know these shortcuts, you would have to take this and put that into that.
The limit, yes. And then 30 minutes later, right? Carpal tunnel and everything else. Just amazing. That limit definition is awesome for killing time and carpal tunnel. It's like, does wonders. Now you have these shortcuts. Obviously, these shortcuts are not going to work for you if you don't learn them. You have to memorize these. There is no reasoning with these. Now, we're kind of lucky that a single equation, ix to the n, takes care of 3 types of functions, right? There is one situation here that I would like to address before anyone goes nuclear, which is when you see the derivative of 4 divided by, let's say, x to the 6. What would you say would be the first step for a problem like this?
Rewrite it. Put the x up.
Rewrite it, put the x up. Okay, that's the same thing. Anyone else? Take the 4 out. Good. So, kick the 4 outside. Guys, you are now in Calc1. This is the last train for you to learn that a over b is the same as a times 1 over b. This number in the numerator can be peeled off. And if it's a constant, it gets kicked out in front of the derivative, and you have to worry about just x to the negative 6. So let me put this nugget of ancient wisdom over here in a box, right? It will show up later when we do integration. You will have a choice of writing an integral like this, dx over x, and then you can write it also as 1 over x dx. Same thing, right? But it freaks people out. And I don't know why. It's just, you just separate the fraction. Just take the numerator times the rest, right? So it will come back. This orange box is coming back. Right now we are working on this mundane problem over here, so sure. But it's coming up. So I kick this 4 outside, right? And I have my negative 6x to the negative 7. And that's going to be negative 24 x to the negative 7, which now it's negative 24 over x to the 7. Cool, right? So now you should be able to calculate a whole bunch of derivatives using this shortcut method. The next concept in this lecture is higher order derivatives. higher order derivatives. What we learned so far is what we say the derivative of f of x, also known as the first derivative of f of x. How many derivatives does f of f have? Infinitely many, exactly. There is the first derivative and the second derivative and then the third derivative and the fourth derivative and the fifth derivative and the sixth, right? And go and on and on and on. The notation for these derivatives is going to be, in the beginning, you have f of x, then you have f prime of x, then you have f double prime of x for the second derivative, then f triple prime of x, and then finally the 4 in parentheses, like that. F of x. And then f of the fifth derivative also in parentheses. Going on 3 dots, f in the n, the nth derivative, which maybe you need to go all the way to 100 derivative for absolutely no application or reason whatsoever. But you can, right? And so on. Compatible notation, y, y prime, y double prime, y triple prime, y to the 4th derivative. The difference between y to the 4th and y to the, it's a 4th derivative. Not the same thing, right? The one on the left means y times y times y times y. The one on the right is the 4th derivative of y. And now we get to the God tier notation. And that's the Leibniz notation with these. If I have f of x, that's the first one. And then the next one is going to be the derivative of f of x. And then the next one is d squared over dx squared of f of x. And then the next one is d cubed over dx cubed of f of x. Dot, 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 going on forever. Now, this notation is awesome. There are no little tick marks that you have to count, right? You just look at the number and you know, right? It says 2 over there, it's second derivative. Now, why is this notation this way? Well, let's like look at this one. And it's really cool. Look. What is d squared? That's d times d, right? And what's dx squared? It's dx times dx, right? And you have over here of f of x. So now what you're going to do is you're going to associate this first, and that would give you your first derivative. Let's call it f prime. And then you are going to, in the next sweep, hit it again with the first derivative to get the second derivative. It also serves as a roadmap to tell you how to get to the second derivative, third derivative, fourth, and so on. Every derivative is always the first derivative when you look at the function before, right? Let's go and look at this. Say I have f of x is equal to 6x to the 4th power. I can calculate derivatives. We can let's use f prime this time around. So f prime, which is the first derivative, is 24x cubed. Beautiful. What's the f double prime? Well, the second derivative is the first derivative of the first derivative.
Say that one more time.
Second derivative is the first derivative of the first derivative. So you're taking derivative of the previous function you have, right? So 24 times 3, 72x squared. Beautiful. What's the third derivative? Third derivative is the first derivative of the second derivative. Exactly. Come on, guys, right? Third derivative is the first derivative of the second derivative. It's just the function before. So 144 x. What's the fourth derivative? I just want words first.
Wow. The first derivative of the third derivative.
Yes, the fourth derivative is the first derivative of the third derivative. Good. So 144. What's the fifth derivative?
The third derivative of the second derivative.
Which is actually true. The fifth derivative is the third derivative of the second derivative. Yes. Amazing. Love it. 100% of what you said is correct and useless. Yes. 0. It reminded me of this cheesy joke where I can't remember it now. It's cheesy. Give me 1 minute. What's the sixth derivative over here in this particular case? 0. How about the 117th derivative? 0. Yeah, you get the idea, right? All right. So now we know all of these derivatives. So is it always going to be like this? You keep taking derivatives and it always kills it? No. Right? To contrast this, you can enjoy the, let's say, f of x is equal to 1 over x. The first derivative is negative 1 over x squared. Second derivative is beautiful, right? So do we see now that as we are taking derivatives, it's picking up powers, right? So you cannot memorize, oh, as I take a lot of derivatives, it's just going to kill it. No, in this case, it's picking up powers, so it's just going to, every derivative is going to bump it up a power, right? I have an interesting question. What is the 265th derivative of e to the x? Is e to the x, right? I know. So, oh, I wrote that wrong. So, 265th derivative of e to the x is e to the x. Now, for those of you that are mathematically inclined, I can ask another question. We're going to think a little bit about this one. What is the seventh derivative of e to the 2x?
The 7.
Yeah, that guy right there. You want him in all of your lab groups, right? It's 2 to the 7th e to the 2x. Because remember what e to the ax does. Every time you take the derivative of e to the ax, it spits out a. So how many a's are going to be? 7 of them, right? So 2 times 2 times 2, so 7 2's every time you take the derivative. Now, you can actually do that step by step, right? But then I change your exponent over here to 79, and you go like, no, I'm not writing that out. And that's the higher order derivatives. So you can have a single function. The function can be multiplied by a constant. You kick that out, deal with the function. Then you can have them added and subtracted right on the pile. deal with each one. We'd say that term-wise. So each one of the terms will be taken care of individually. And then we have the higher order derivatives. We need higher order derivatives because the world around us asks for them, right? So we are going to learn very soon, which is next week. When we deal with a little bit of motion, we'll have a section where we'll learn derivatives and rate of change. We will learn that the position function is your f of x, and then velocity is the first derivative, acceleration is the second derivative, jerk is the third derivative, and so on. Going down the line is more, but generally we only take care of the first three, and that's technically what. So obviously I'll explain all of that when we get to that section. So this is it for 3.3, right? Those four formulas, they're introduced, they're all short. I've never done this. I've been teaching with the projectors. So all of those formulas there, you have to memorize. And again, that's the trade-off. You are memorizing those formulas so you don't have to crank that limit formula, right? That will take forever to compute. I mean, imagine just imagine the insanity of computing, right? Expanding x plus h to the 7 minus x to the 7 divided by h, right? Coming back later on, right? Exhausting calculations. I don't have a close here.
Smash the like button.
Oh, smash the like button. Yes, there we go. Smash the like button. Subscribe and see you, right?